Hello guys, so in this video we're going to go over our concept of how to compute cylindrical coordinate triple integrals. So basically the idea is that the cylindrical coordinates basically follow the same principles as triple integrals, except we have to convert them to cylindrical coordinates. Given right here, we have our conversions. We have x squared plus y squared is equal to r squared. That one you should already know. Notice our dv, r times dz times dr times d theta. And notice the r right here. The r is called the Jacobian, and you have to include it in your dv, because if you don't include it, you're going to get the wrong answer. And the x and y conversions, you already know them. We're asked to compute a region bounded by z is equal to 0, z is equal to 9 minus x squared plus y squared, and it's a full circle on the xy plane. And we're given the function of 3x squared plus 3y squared times dv. And we're going to compute this using triple integrals. So we're asked to compute the cylindrical integral bounded within the region. And we have the formula right here. And we have the conversion factors. So let's get right to it. So the first step we do is we identify our f of x, y, z and our dv. Basically, we're going to identify the variables of integration and then plug them into the cylindrical coordinate triple integral. So f of x, y, z. Our f of x, y, z is literally just the function given to us. So it's 3x squared plus 3y squared. And our dv is also already given to us, so it's r times dz times dr times d theta. But a lot of times you skip these steps and then you get the problem wrong, so that's why I like to go from the very basics. And in step 2, we're going to convert to cylindrical coordinates. So how do we do that? Well, our f of x, y, z, we want it in terms of f of r theta z, because that's essentially cylindrical coordinates. So our f of x, y, z is equal to 3x squared plus 3y squared. So we can simplify this by factoring out a 3, and we're left with x squared plus y squared. And now it's starting to look like we can convert this to cylindrical coordinates, because we know that x squared plus y squared is equal to r squared. So we can substitute r squared in there. And thus f of r theta z is equal to 3r squared. So now that we have it in cylindrical coordinates, now we can move on to step 3. So now for step 3, we're going to find the bounds of integration. So we know that the region is bounded by 0, z is equal to 0, and z is equal to 9 minus x squared plus y squared, and it's a full circle on the xy plane. So how do we interpret this information? Well, let's start off with our z bounds. So we know that the initial bound is, the lower limit is 0, because it tells us the upper limit is given to us as 9 minus x squared plus y squared inside the square root. But notice how we converted, everything needs to be in cylindrical coordinates. We want everything in terms of rho of r theta z. So we're going to convert this to cylindrical coordinates. So 9 minus x squared plus y squared is 9 minus r squared. And we know that the square root and the radical can cancel each other out. So we're left with z1 is equal to 9 minus r. So our z bounds are from 0 to 9 minus r. And now for our r bounds, we're going to solve r from z. So we know that our inner lower r bound is equal to 0, and our upper r bound is equal to 9 minus r. So what we want to do is set this equal to 0 and solve for r. When we do that, 9 minus r is equal to 0. We know r is going to be equal to 9. So thus our r bounds are from 0 to 9. What about our theta bounds? Well, keep in mind that it's a full circle on the xy plane, as mentioned. So since it's a full circle, we know that our initial theta is 0. And since it's a full circle, not a half circle, not a semicircle, not a quarter circle, we know that our second theta bound is 2 pi. Thus our theta bounds are from 0 to 2 pi. So now that we have this information, now we can set up our cylindrical coordinate integral. So we know the formula is the integral, the volume of this is of f of x, y, z of dv is equal to 3r squared, which is our f of x, y, z, or f of r theta z, And then our dv is r times dz drd theta. And how do we know which boundaries come first? It's the same way as with the triple integral. Whichever one has the most variables is typically on the inside, whichever one has the least is typically on the outside. Also, whenever we're integrating with respect to cylindrical coordinates, usually theta is always on the outside. And we know that 0 to 9 is less variables. The r has less variables than the z. So 0 to 9 will be our middle bound. And then our inner bound is 0 to 9r. Why? Because 9 minus r has the r variable. So we definitely don't want that on the outside. We want that on the inside. So our z limits are in the inside because they have the most amount of variables. More variables, we want to have those towards the inside. So now that we have our bound set up, all I'm simply doing is multiplying the r squared right here with the r right here. So 3r cubed dz dr d theta. And remember, the r is that extra r right here is called a Jacobian. All you need to know is that it's part of the dv. So do not forget it, because initially people forget. So we know dz bounds are these, 0 to 9 are. Our r bounds are from 0 to 9, and our theta bounds are from 0 to 2 pi. So now let's integrate this. So now we're going to integrate this and solve. So our integral, we're going to factor out the 3. So 0 to 2 pi, 0 to 9. And the inner bounds that we're going to work with right now is the z limits. So 0 to 9 minus r cubed dz dr d theta. So notice how I separated the dr and the d theta from the integral. That's because I don't want you to accidentally integrate with respect to r, because it's very tempting to integrate with respect to r because you're given r cubed. But know that whenever you do this method where you separate them, where you just kind of put them off to a side and you have what you're focused on towards the middle, it'll minimize your error. So no, do not integrate with respect to r. Common mistake. So now we're going to integrate this. So with respect to z, it's r cubed times z, bounded from 9 minus r to 0. So now what we're going to do is we're going to treat the 3r cubed as a constant, because the r cubed is technically a constant. It's not a variable, because we're integrating with respect to z, and our bounds are z, which are 9 minus r to 0. And then 3r cubed, now we're going to plug in the bounds. 9 minus r is our upper limit minus our lower limit, which is 0. And we know that's just going to 0 out, and we're left with 3r cubed minus r to the 4th. And all I did was just distribute the r cubed, nothing more. I didn't distribute the 3, I only distributed the r cubed. Why? Because the 3 is a constant, so there's no point in distributing it back. However, now that we're going to integrate with respect to r, I distribute the r back in. So now we have the integral 0 to 2 pi. Now we're integrating with respect to r. So 9r cubed minus r to the 4th dr d theta. I separate the theta so we know we're focused on integrating with respect to r. So what we do here is we're going to integrate with respect to r. So we know 3, 9r cubed integrated is r to the 4th over 4 minus r to the 5th over 5, bounded from 0 to 9. So now what I'm going to do is I want to have a common denominator so that way I can factor it out, because it makes it easier when you're plugging in numbers. So I always highly recommend this method, or at least get comfortable with it. Just make sure you don't mess up. So that's what I'm about to do. So 9 over 4 times 9 to the 4th minus 9 to the 5th over 5 minus 9 to the 0 4th minus 0 to the 5th over 5. And these 0 out, and we're left with 3 times 5 over 5, and this is what I was talking about, times 9 to the 1 times 9 to the 4th over 4. So all I'm doing is I want to have the same denominator. So I'm multiplying by a fraction that will give me that, minus over here 4 over 4 times 9 to the 5th over 5. So all I did right here was nothing more than just try to have a common denominator. So I'm multiplying by two fractions that are equal to 1, so it doesn't change the value, and I'm going to have a common denominator, minus 0. So I know this term goes to 0. So 3 times 5, 9 to the 1 times 9 to the 4th is 9 to the 5th over 20 minus 4 times 9 to the 5th over 20. And notice how I can factor out into 9 over 5th, and I can factor out a 20. So I factor out a common denominator of 20 and then a common factor of 9 to the 5th. And what's left inside is 5 minus 4, which is equal to 3 times 9 to the 3 squared to the 5th power, because 9 is essentially 3 squared. Why am I doing this? So I can further have this simplified. Of course, you don't have to do this, but it makes the algebra a lot easier. So don't do it if it's going to make you mess up. But just know that 9 is equal to 3 squared, and I want to have a common base of 3. And I know 5 to the minus 4 is 1. So that's why I do this, so I can simplify this. So I know 3 to the 1 times 3 squared to the 5th power is 3 to the 10 over 20. And I know I can rewrite this as 3 times 1 times 3 to the 10. We add the exponent, so we get 3 to the 11th over 20. So now let's integrate. We're going to integrate with respect to theta. So we have a constant of 3 to the 11th power divided by 20. And we have an integral of 0 to 2 pi. And we don't have any active terms for theta, so we're just left with d theta. So when we integrate this, we get 3 to the 11th over 20. Divide with the integral of d theta, it's just theta from 0 to 2 pi. So now what I'm going to do is I'm going to plug in the bounds. So I know 2 pi minus 0. And furthermore, I want to simplify this. We get 3 to the 11th minus 20 times 2 pi. And the 2 and the 20 can simplify to be 3 to the 11th divided by 10 times pi. And that's the final answer for this cylindrical integral. So basically in step 1, we identified f of xyz in our dv, which has a Jacobian of r, so do not forget that. In step 2, we converted to cylindrical coordinates. Step 3, we identified the limits. So the limits can be kind of trivial. It really requires you to read the question. So understand the region being bounded is the limits that you're going to compute. From there, we set up our integral, and then we basically just computed from there as if it were a triple integral, but so with the cylindrical coordinates. So that's a big difference now. It's cylindrical coordinates instead of x, y, z. So let's move on to a different example. In this example, we're asked to compute the cylindrical integral bounded within the region of 2x plus y minus z, bounded below z squared is equal to x squared plus y squared, 9x squared plus 9y squared, within the cylinder of 36 is equal to x squared plus y squared. So now what we're going to do is, for step 1, we're going to identify f of x, y, z, and dv. And this step is very easy, straightforward, but identifying the variables and setting up the integral makes it a lot easier to compute and makes it less error prone. So f of xyz is just what's given to us in the problem statements. On this case, it's 2x plus y minus z. Now, our dv is equal to, we can look it up right here, it's given to us in our conversions. It's r dr dz dr d theta. So that's our dv. And it's always going to be that, so don't worry about it being anything else, at least for Cal 3. And in step 2, we're going to convert to cylindrical coordinates. So our f of xyz, we know our x is our cosine theta, and our y is our sine theta. So we know that 2x plus y minus z, and we know x is our cosine theta, and we know y is our sine theta, and z is z for both x, y, z, and for cylindrical, so we're going to leave it as z. However, now we're going to leave this as 2r cosine theta plus r sine theta. And you might ask yourself, what's r? Well, let's keep going. Let's keep moving forward now. So let's move on to step 3. So now for step 3, we're going to find the bounds of integration. So we're going to start with the z-bounds. So we're given the region z squared is equal to 9x squared plus y squared, 9y squared. It's above z equals 0. So right off the back, we know that our lower z-bound is 0. And our upper z-bound is z squared is equal to 9x squared plus 9y squared. And we know our z squared is equal, we can factor out the 9 and we're left with x squared plus y squared. And we know from our cylindrical coordinate conversions, we know x squared plus y squared is equal to r squared. So we know z squared is equal to 9r squared. And we know that we can take the square root of z squared and we can take the square root of 9r squared. Okay, so when we do that, we know our z is equal to the square root of 9r squared. The square root of 9 is 3, and the square root of r squared is r. So z, the upper bound, is equal to zr, 3r. So our z bounds are from 0 to 3r. So what about our theta bounds? Well, we know our lower theta is 0, and our upper bound, since this is a full cylinder, not a half cylinder, never specified it's a proportional cylinder, it's a full cylinder, we know our upper bound will be 2 pi. Always assume it unless otherwise stated. But since it's telling us it's a cylinder, we assume it's a full cylinder. So our theta bounds are from 0 to 2 pi. So now let's compute the r bounds. So let's find the r bounds within the cylinder. So we know x squared plus y squared is equal to 36. So we know that our inner bound is 0 because it's not specifying what it's within the cylinder. So it's specifying that our initial, it doesn't specify another cylinder that's centered at the origin. So our r is 0. Our r1 is equal to x squared plus y squared, which is equal to 36. Thus our r1 is equal to x squared plus y squared, which is equal to r squared. So we know r squared is equal to 36. So when we square root both, we know that r is equal to 6. So thus our r bounds are from 0 to 6. So now in step 4, we're going to set up the integral. So we know our outer bounds are 0 to 2 pi. Our r bounds are from 0 to 6. And since our z has the most variables, it's going to be our inner bounds from 0 to 3r. So we know 2r cosine theta, our f of x, y, z, f of r theta z, 2r sine theta minus z. And then the dv, which is r dz dr d theta. So that's our integral. So first we integrate with respect to z, then with respect to r, then with respect to theta. So let's go ahead and integrate this function. So now that we have our integral, we're going to go ahead and integrate and solve. So our integral from 0 to 2 pi, 6 to 0, 3r, given 2r cosine theta plus r sine theta minus z, r dr dz d theta. So notice that r is a Jacobian, so don't forget to include it, because I will stress it again because people do forget to include it and then or they don't know where the heck it's coming from. So just don't forget about it. And note that we're integrating with respect to z. So when we integrate with respect to z, we can just leave the r out for now because it's just treating as a, we're going to treat it as a constant. So 2r cosine theta times z. In the middle term, or the r sine theta, is r sine theta. And then we integrate with respect to z, it's z minus z with respect to z, we integrate it's z squared over 2, bounded from 0 to 3r. So now we're going to plug in the points. So 2r cosine theta 3r plus r sine theta 3r minus 3r squared over 2. So all I did right here was just minus 2r cosine theta, 2r times r sine theta times 0 plus 0 squared So all I did right there was just plug in the 3r and plug in the 0. So now we're going to distribute the r to each term because now we have it in terms of r. So we're going to distribute the r out to each term. We know all of these terms go to 0. So now in our new integral, it's 2 times 3 is 6, and we have 3r, so it's going to be r cubed cosine theta plus 3 r squared, because we have 2 r's, sine theta, minus 3r squared is 9r squared over 2. Note that we're only squaring the top, not the bottom. That's why I put parentheses, because you can slip here. We're only squaring the top. So that's why I put parentheses around the 3r. So it's 9r cubed, because we're distributing 9r squared multiplied by the r coming from the outside. It's 9r cubed over 2. Of course, minus 0. So this term goes to 0. So now let's integrate with respect to r. So now we're going to integrate with respect to r. So the bounds for r were 0 to 6. We're left with 6r cubed cosine theta plus 3r cubed sine theta minus 9r cubed over 2 dr d theta. And we're integrating with respect to r. So in doing so, we can factor out a 3 out of every single term. So we're going to go ahead and do that to make this simpler on us. And we're left with 2r cubed times cosine theta plus r cubed times sine theta minus 3r cubed over 2 dr d theta. So now we're going to integrate with respect to r. So 3, we're integrating with respect to r is 2 cosine theta, because we treat the cosine as a constant, r to the 4th over 4, plus sine theta, because it's a constant, r to the 4th over 4, because it's r cubed, minus 3 over 2 is a constant, r to the 4th over 4, bounded from 6 to 0. So now 3 over 4, 2 cosine theta, and all I did was factor out a 4 out of every single term, because we can do that since there's a common denominator of 4 for every single term. Sine theta r to the 4th minus 3 over 2 r to the 4th, bounded from 6 to 0. So now what we're going to do is, notice how each term has r to the 4th. So we're going to factor out an r to the 4th. So 2 cosine theta plus sine theta minus 3 over 2 r to the 4th from 0 to 6. Why do I do this? Because it makes it a lot easier. So we can just treat all those terms as constants and plug in the bounds with respect to just r. And I did this because they're all the same term, r to the 4th power, so we can factor this out. In doing so, 3 over 4 plus this constant, 2 cosine theta minus sine theta minus 3 over 2, we can plug in the r bounds, 6 to the 4th minus 0 to the 4th. And of course we know that term zeroes out, and we're left with 6 to the 4 times 3 over 4 multiplied by what's in the brackets, 2 cosine theta plus sine theta minus 3 over 2. Now we can integrate with respect to theta. So given now our integral, 6 to the 4th power times 3 over 4, 2 pi, and then we're living 2 cosine theta plus sine theta minus 3 over 2 d theta. So now what we're going to simply do is we're going to go ahead and integrate this. So 6 to the 4th times 3 over 2, and we're integrating the cosine theta. So I've kept the constant out, so 2 cosine theta, the integral of that is sine theta in the green parentheses, plus sine theta, the integral of that is negative cosine theta, and then minus 3 over 2 times theta. And this is being bounded from 0 to 2 pi. So now what we're going to do is we're going to have a common denominator of 2 from each term, so we can simplify this a little bit. So we know 2 over 2 times 2 sine theta plus 2 over 2 times negative cosine theta minus 3 over 2 theta. And why am I doing this? I'm doing this so we can factor out a common denominator because it makes it easier when we plug in the bounds. It always does. So we can pull out the 2 in the denominator, and we're left with the numerator 2 times 2 is 4, 4 sine theta minus 2 cosine theta minus 3 theta, bounded from 0 to 2 pi. And now 6 to 3, 4 times 2 is 8. We're left with 4 sine of 2 pi minus 2 cosine of 2 pi minus 3 2 pi minus 4 sine of 0 minus 2 cosine of 0 minus 3 of 0. So all I did was just plug in everything. This zeroes out, sine of 0 zeroes out, 3 to the 0 zeroes out, and I get this from the unit circle. And now we compute in my calculator. 6 to the 4th times 3 divided by 8 gave me 486, and we're going to ignore all the zeros, so we're left with minus 2 times cosine of 2 pi is 1 minus 3 times 2 pi is 6 pi, and in the other brackets we're left with 2 times cosine of 0, which is 1 times 2. So 486 minus 2 minus 6 pi plus 2. So the 2's can cancel each other out, and we're left with 48 times negative 6 pi, which is equal to 2916 pi. So that's our final answer for this cylindrical integral. So basically just apply the exact same process we did previously. So we're converting. So we identify f of xy, dy. We're converting to cylindrical coordinates. The most trivial part is identifying the bounds of integration. And you can do that by reading what the region is bounded by and just kind of visualizing it. And from there, you treat it as a triple integral and you integrate with respect to r, theta, z. Thank you for watching. I hope this was helpful. If it was, please feel free to like, subscribe, comment, and share, because I do have a bunch of videos on calculus, and I will have a lot of STEM videos on this channel. Thank you for watching.